Um, the talk will be in English. By the end of the talk, there will be like a specific time for questions, and you are free to ask them in Spanish or English. It's fine by me. I'll answer in whatever language you choose to use. Most of my slides are, well, every slide it's in English and it's supposed to be in that one. Okay, can you confirm me you can see my screen? Okay, cool. Okay, so I've been invited to talk about a bit of interpretability in NLP. So this talk is titled Interpretability and Analysis, an overview and its impact. So this talk will be divided in two parts. The first part is just an overview on what's actually interpretability and analysis in NLP, and the second part is just measuring its impact, which is a work I've been doing, and we just sent a paper for EMLP, so hopefully it gets up. Anyway, so let's start. Um, we all know that the impact that machine learning is having on the world is huge. So I could give the classic example of ChatGPT. We all know this. It's nothing very specific, so I'll not get too much into it. Um, but they are black boxes, right? Right? Like we largely do not understand how these models work. I mean, that's not exactly true. We do understand the algorithms we use to make them learn, but not what they are actually learning. So although we can understand the updates that they make step by step in this training phase, uh, the overall things that they learn by the end of the training, it's largely unknown. Uh, that can be scary in a lot of sense. Um, so as the capabilities of these models get improved by the second, so the risk associated to the use of these models gets bigger, right? So we've seen how ChatGPT itself has grown in capabilities since the start of it. Nowadays, these models are quite popular and their use has been quite distributed. And the fact that we don't really understand how do they actually make predictions can be riskful. So understanding what these models actually do seems like a good way of understanding the risks and hopefully mitigate them. And that's the focus of this AI safety initiative, right? So it's useful to understand these models and to actually know what the risks are. There is actually research into understanding the inner workings of this model. This research is, unsurprisingly, interpretability and analysis. Um, so in this talk, I'll just call it interpretability or just interp, just to make it shorter. But don't forget this analysis part because this analysis part is not, uh, it's important. But what even is interpretability analysis research, right? Because this concept is very broad and it needs to be grounded in something. And many definitions have been proposed, and there's no gold standard in what the actual definition is. The definition I'm going to take in this talk, it will be that it's any work that develops a deeper understanding of the behavior or inner workings of NLP models, methods, or systems. And specifically in this talk, I'll focus on the inner workings part. So we'll just focus on what is the actual computations that these NLP models can make. And as a disclaimer, most of this area is now called mechanistic interpretability or just MERC-interp. Um, I am not a particular fan of this terminology. I believe this term to be very overhyped, and I think it's not very useful for the community to have a lot of hype in some area of research when it might not deliver the amount of expectations it's actually building. So I'm not usually using mechanistic interpretability concepts. I mean, the concept of mechanistic interpretability. I just call interpretability as a general. Um, but it's useful because if you actually want to search information about this research area, you should Google mechanistic interpretability and you'll find a lot of work. As I said before, this talk will be organized in two main steps. The first step is just I'm going to talk about three main results in interpretability research that have been quite impactful, and I think they're useful for everyone to know about. Even if you do work on research in machine learning, and if you don't, it's still interesting to know a bit about how these models work. Um, and the second part of this talk will be what's the actual impact of the research in interpretability. So the explanations of the three results are based in the survey by Javier Ferrando. This survey is really, really good. It's a survey that just analyzes all the research that has been going on into inner workings of NLP models, and it's highly recommended to get into the area. So if you have any curiosity into actually get into this sort of research, I would recommend a lot reading this survey. This survey is really, really good. Um, but first, I know many of you are not that familiar with machine learning research as a general, and it's very important to understand the intricacies of the transformer model, which is basically the architecture that has taken over all of these kind of big machine learning models. So ChatGPT is a transformer, DALL-E is a transformer, everything is a transformer nowadays. So it's very useful to understand a bit of how this transformer architecture is organized, and that way we can analyze it deeply better. So this is the transformer architecture. So if you are into machine learning research, you'll read Vispani et al. Like quite a lot. Um, anyway, this architecture is basically used in everything nowadays. It's very famous. As a random fact, I actually met one of the authors of this paper here in Japan, um, which is totally unrelated, but I try to mention that every time I can. But yeah, as you see, this architecture can be quite complex if you're not into machine learning research. And we'll have a simplified notion of this architecture of this talk. So it's not important to actually understand this, but rather understand the second kind of illustration I'll give, which is this one, much simpler, right? So there, in a transformer block, we'll have one self-attention layer and one MLP layer. And these connections that kind of skip the actual weights of a matrix. So we have activations here from the model. These activations go through the self-attention and also skip it, then get added here. And then again, the same with the MLP. And how transformer models work is that you grab a lot of these blocks, put them like one on top of the other, and that's how you get basically a model nowadays. So once again, MLPs and self-attentions are alternated, and what we call a pair of these MLP and self-attention is just a transformer block. And there's another detail is that when we have an LLM, we want to change, this is a model that grabs text and outputs text, right? So how can we do that? We have this tokenizer and embedding matrix. What this does is that it grabs text, it tokenizes it, doesn't matter what that means actually, but it changes this text into activations or vectors. So we can represent activations of vectors like this. This would be our representation of what activations actually are. And we also have another layer, another component of the model that is called the unembedded matrix and the softmax. So this, what it does is that it takes these activations and maps them back to the token space. So we get a particular percentage of what's the next word for this sentence. So we have this is and the predictions would be an example. That might be the next word predicted for this sentence. Amazing, elephant, or whatever, right? So we get like a distribution on what are the most likely next words for this sentence. Again, this embedded matrix maps tokens into vectors. You can understand tokens as words. So it maps words into vectors, and this embedding matrix maps activations to probabilities of tokens or words. Okay. So a transformer model in general is just this. It grabs the text, it goes through the embedding matrix to get activations. Then it goes through a series of these transformer blocks, and afterwards it gets mapped back to the token space by this embedding matrix. And we have a distribution on what the actual next word for this sentence is. And that's how ChatGPT generates the next token, right? So it continuously generates the next word one by one. So now that we have this notion of how these models kind of work, at least how these are structured, now let's start to actually understand in practice how these components work. So the first result I want to talk about is the residual stream. Machine learning has for a while the concept of residual connections. Uh, this is the idea that you skip a layer in a connection. So for example, this is an image of the original paper of the residual connections. They had activations here and they just skipped all these weight layers and just added them back at the end. So there, the same activation gets split in half, one that goes through the weight layers, and another that just skips the weight layers and it gets added back at the end. And this idea has long survived the test of time. So it has been used. This paper was from 2015, if you've seen, that's quite a long time ago. And it's still being used like in most architectures today. So it's very common to see this idea of the skip connections or the residual connections. And actually, if you see the transformer blocks has them, it's right here, right? You can skip the self-attention block and you can skip the NLP block. And that's basically a residual connection. What this residual stream interpretation does is that it changes our illustration of the transformer from this to this. So as you see, it's exactly the same thing. So you see that the activations get split in half. One goes through the self-attention, the other doesn't, and then gets added. But the difference is that what we understand as the main kind of path towards the end is not going through the layers. It's actually just keeping everything. And these weight matrices are just on the side. So these matrices actually read and write from this line that goes straight from the activations in the input to the activations in the output. And this line is what we'll call the residual stream. So this is a stream of information where we have layers that read and write to it. In this case, the self-attention and the MLP layers. This was started by Anthropic in their landmark paper in 2021. And it sees this residual stream as a main component of the transformer architecture. And these MLPs and self-attention blocks just read and write from the residual stream. So for example, we have this residual stream, right? We have some sort of activations here. The self-attention just reads the value from here. It computes something and it adds it back to the residual stream, changing very slightly the activations in the actual residual stream. So each of these self-attention and MLP blocks actually does very little in terms of the activations. And there is evidence that this is the case in LLMs. So LLMs actually have like a very strong start in the residual stream, in what the actual prediction of the next word is. And each consecutive self-attention and MLP layer is making very slight modifications into the prediction of the next word. So you can actually see that the predictions from the start to the end is actually being built upon by promoting certain concepts and certain tokens in this space. So a very related result that is very important for this is that MLPs can be seen as key value memories. So in here we saw like the effect of the self-attention, but now we'll see kind of the effect of the MLP. So there has been evidence that the factual knowledge of the model is being encoded in the MLP layers. So for example, when you prompt a model to ask what's the capital of Italy, right? It has to answer Rome, but it cannot logically deduce that. It has to be stored somewhere in the model, the fact that the capital of Italy is Rome. It's just a fact. And there has been evidence to suggest that these facts are stored in these MLPs. So how this works is that these MLPs kind of read this Italy plus capital idea and they output Rome. Okay, so we know that Italy plus capital, it has to be output as Rome. And they work as a key value memory. So for a specific key, they have a specific value. In this case, the key would be Italy plus capital, and the value would be Rome. And the thing is, this is actually often interpretable So if you actually see the activations here by the end of the MLP, you could actually read Rome, which is very interesting. The fact that you can see the activations in the middle of the model and actually read the word Rome. Uh, it's not often that nice, but it can be sometimes. Um, and yeah, there is evidence to suggest that it kind of works like this. But we'll go into the details of how this process actually works. So an MLP is just three main components. An MLP is just an input matrix. So we have the input matrix here, an activation function. So we have the rel function here. For those who don't know that much about machine learning research, what this does is just it gates some of the activations before and only lets some activations go through. And then we have an output matrix here. Okay. So again, these two are matrices. So matrices, as you've seen in linear algebra. So these are just basically a rectangle of numbers. That's all that it is, both of these. Um, and in practice, they work as key-value memories, which is very interesting. So if you see the input matrix here and you analyze a certain row of this would be only a sequence of numbers, but this sequence of numbers can actually encode a specific concept. So in this case, the capital of Italy might be encoded in one of these rows. And although it means like you would just read a sequence of random numbers, these random numbers actually represent this Italy plus capital concept. Um, and what I found is that also the the columns in the second matrix, in the output matrix, would represent another concept, basically the value associated to this key. So Italy plus capital would get mapped to Rome. Again, in this case, I transpose the matrix to write it horizontally, but this would actually be the columns of the original matrix, right? So if you transpose it, the columns turn into rows. That's why I put Rome in a row instead of in a column. Yeah, but it's interesting because I've talked about how this worked, but I've not talked about how they actually found this because it's not easy, right? These are just numbers. How can they suppose that these numbers actually mean Italy plus capital, and how can these numbers mean Rome? You can just try to. It's not easy to know how this works. How do they test this? So they decompose the outputs from this layer into the specific columns of this matrix here. And what they do is that they map it back to the token space. So you remember we had the unembedded matrix, right? This unembedded matrix could take activations and map it back to the token space. And this is a part of the model that is usually used at the end of the model to actually like perform this kind of computation on the prediction. But you can grab that unembedded matrix and just plug it in here, like in the middle of the model, and just see what the tokens being promoted are. And what you can see is that this can actually represent this concept of Rome, and here it will represent the concept of Italy plus capital. So that's a way to actually look at the predictions or look at what the model is thinking in a way. Again, this in practice does not work as cleanly as this. Like you wouldn't actually get like the actual prediction of Rome. You have to do like a lot of different hacks to actually see what this model kind of is thinking, and it doesn't work as cleanly as just in one MLP layer, then the fact is encoded or whatever. But you can think of it like this, and it's kind of true, but it's not that clean. And so when they map these activations to the token space, they notice common interval patterns. For example, they mapped the one of these rows here, and they saw that it it got associated to the concept of measurement. So, for example, the tokens that got promoted in that place were kilograms, percent, spread, total, yards, pounds, hours, which are just measurement words, right? So it gets promoted those kind of words. Another concept that they found is the WH relativizer. So these kind of words, which are all syntactically and semantically were related. And another concept that they found is just food and drinks. So the concept that got predicted would be drinks, coffee, tea, soda, burgers, whatever. So they are roughly interpretable at times because again, this is not like like a that exact of a science. These are just findings that they've been finding, and they are very cherry-picked examples, but they are very interesting cherry-picked examples. And another result I wanted to talk about is the one of superposition and sparse autoencoders. So ideally, we want each neuron of a model to represent a single feature, right? So if one neuron is mapped to a particular concept, it would be quite easy to interpret the predictions of a model, because you can say, okay, this neuron means food, or this neuron means whatever, and we can kind of understand what the model is thinking in a way. But this is not the case. Like, models do not work in that way at all. So neurons are not usually associated with one particular concept. It's just not like that. How has been found that it's kind of a more realistic notion of how these models actually work is with the concept of superposition. It's the concept that the model is representing more features than the actual dimensions the model has. So in this case, this would be a model without kind of superposition, without interference. So this means that we have four different dimensions. In this case, well, the four dimensions are represented in a 2D space, but it doesn't matter. Um, and each dimension would be associated to one specific concept. So we can clearly kind of separate what each dimension means, right? So this dimension might mean food, this dimension might be drinks, and whatever, right? So it would be quite easy and quite uh, easy to understand the predictions of a model if the model actually worked that way. But it's not the case. It has been found that it's closer to this, where you have some certain number of dimensions, and the model wants to represent more features than the dimension it actually has. So these dimensions are not exactly orthogonal within each other. So you get interference. That means that one dimension has also a bit of the component of another dimension of another feature. So for example, in this case, this might be the concept of food, this might be the concept of drinks, and they have some sort of interference, some sort of common kind of common representation in this vector space, and it's not completely orthogonal. Um, and this is hard because we actually want to interpret or decode this information, right? How can we decode features if they're interfering with another? It's super hard. And actually, it's a really hard area of research to get into on how to actually do this. But there has been recently some results on this. This is with sparse autoencoders. This work has been mainly been led by Anthropic. Once again, they have been doing a lot of this mechanistic interpretability kind of work. Um, and what they do is that they train an MLP. So an MLP is, again, a small machine learning model. Upon the activations of an LLM, so they add another model into the original large language model. And this small model is trained to reconstruct the original activations, but with a sparsity bottleneck. So how does this work? We have an original activation of the model. This goes through an encoder matrix, which actually it maps these original activations into a larger space. So in this case, we have like 4 dimensions here, right? And we map it into a vector that has now 6 dimensions. So a very big like much bigger dimensional space. And then you have another matrix which maps this map back to the small dimensions that you had before, and you trying to reconstruct the original activation. So by the end of this model, you expect to have the same activation at the beginning and the same activation by the end. What is the idea behind expanding the number of dimensions? Is that they want to reduce the amount of interference, right? Because if you have more dimensions here, you can reduce the interference within one and another concept in this space. So that's the idea. They want to basically reduce the amount of interference, just mapping each one of these to a bigger dimension space, such that they can actually be orthogonal and we can interpret what is going on. Um, but again, like, if you've ever trained a machine learning model, you know that this kind of training seems a bit naive. Like, it seems way too easy and doesn't seem reasonable. The idea is that why could this be useful is that they are a sparsity loss. So this representation at the middle, this represent it has a very big dimensional space, but they are a specific loss to prohibit this representation from having too many activations. So in this case, you see that these activations are very like grayish. So they have some parts that are very activated, some parts that are not very activated, and yeah, it gets mapped to a vector that has most of these activations completely dead, so they are all white, but some activations are very activated, and this is due to this sparsity loss. So this sparsity loss turns like a kind of a grayish activation into it promotes the idea that we don't want activations that look like this, but rather activations that look like this, where some dimensions are very activated and some dimensions are not very activated. Um, so what they find is that when you actually do this, these activations by the end turn to be very interpretable. So, for example, when you have the text that could be like the capital of Italy, you can map it with this sparse array encoder into a bigger dimensional space, and you analyze the neurons that got activated, and you can try to interpret what these neurons actually mean. You see that this neuron might be only activated when you see Italy related text, and this neuron might be activated only when you see text in English. So it can be more this idea that we wanted each neuron to meet to be represented as one concept is much more likely in these sort of activations than these ones. So these activations tend to be more interpretable, and we can understand what is going on, kind of. Again, this is not perfect science, and it's an ongoing area of research, so it might not always be the case that these neurons are interpretable. Oftentimes it has a lot of limitations. But these are some features that these sparse array coders have found in practice in large language models. So there's like a feature they found where was a feature that only got activated on DNA sequences. So if you have this kind of DNA sequence, like this neuron would fire in every one of these tokens. There was another feature that they found that it would activate only on base 64 strings. So if you have a link like this one, this neuron would activate only when you had like base 64. Um, and you can actually control that. If you have a random model and you activate this feature like manually, let's say, the model would start to predict base 64 strings suddenly out of nowhere. Um, and also they found a feature that also predicted or was activated only in Arabic script. So whenever the model saw Arabic script, this neuron would be fired. Um, so one question is, okay, how can this actually be useful? Uh, I would like the idea of what if we found a line neuron, right? So whenever the model is lying, this neuron fires. Could we actually turn it off? Uh, so that would be like a huge practical implication on this. Um, this research is currently not affecting the state-of-the-art models, so it currently does not work like that. Whenever you see ChatGPT trying not to lie or trying to be safe or whatever, it's not with research that it's inspired by this, but still it has potential to be useful in practice. Okay, so the second part of this talk is kind of forgetting, like I've already given an overview of what the kind of research looks like and some key results on it. But one question is, what's the impact of this kind of research? Because there is actually quite a lot of skepticism in this research area. Um, Machine learning has a long history in research, but we mostly treat like these models as black boxes. We don't really understand what is going on. I've shown some results, but if we try to actually understand what the predictions of a model are actually doing, like we are very far from understanding these models. Um, and due to the incredible success of recent years, like GPT and so on, there has been an increasing interest in this area of research, so interpretability and analysis. Um, and this area of research, interpretability analysis, should in theory be useful for our trust in these models, the implementation of safety guardrails, but not actually everyone thinks this way. So, for example, this is Sarah Kruger. She's a very famous researcher. She has been very successful, and this is just one example of someone who is very very well known into the research in machine learning and who feels that this kind of research is not really useful. And she compares this interpretation of selectivity measures as tea-leaf reading. So she's basically saying this is useless. There are some concerns in this area of research, which are very well founded, I would say. Um, so some concerns is that most of these interpretability results are cherry-picked examples. I've shown you like these Italy plus capital things, but most of these results that are found in machine learning research are very cherry-picked, and you don't see all the negative results you can get from this sort of area of research. And it's true, and it is a problem of the research area. And also, a lot of these results are model specific. So, for example, these parts autoencoders, they are trained on a single model. So if you change your model, you can no longer understand the concepts of another model because that MLP was trained on a single model. So it might not actually generalize to different models, um, which is somewhat of a shame, right? If you have methods that are model specific, then it's not really useful for everyone, right? Um, and also is that most of this area of research has no clear practical implications. So there are no clear. I've talked about a bit about like the what kind of usefulness can this research go, but it's not often clear like what do we actually gain from learning how these models actually work. Um, and it's true, like what is actually the impact of researching interpretability analysis in LP, right? If like these questions are very open questions, then okay, what it's actually the impact? And luckily, we wrote a paper about it. So this is the paper we just recently sent to archive and is now on review for EMLP. So hopefully it gets accepted. And we try to measure what's the actual impact of researching probability analysis in LP. Um, so we try to measure what is the impact that it's having. And measuring impact is something very hard to do, I would say. It's not clear how to measure impact. And we also provide guidelines on what the most impactful types of interpretability and analysis research are. And we also try to give guidelines on how to improve the research to make it less to try to calm the skepticism in the area. So one warning of this paper is that mechanistic interpretability, which is this area of research of understanding the inner workings of models, is just a subfield of interpretability and analysis. So our definition of interpretability analysis goes much beyond research into inner workings of models. There's a lot of research that I've not been talking about this talk that is included in this concept of interpretability analysis. So our definition that we take on this paper is again very similar to the one I've taken in this talk, is that we care about all the papers that aim to develop a deeper understanding on the behavior of inner workings of NLP models, methods, or systems. So again, I've been focusing mostly of inner workings of NLP models, but also understanding methods or systems can be considered part of interpretability analysis. So there's much more work in this area than just mechanistic interpretability. Okay, so how can we actually measure the impact of interpretability analysis, right? Like it's not easy to measure the impact of a whole research area that is having. Um, so what we do is we analyze the citation graph. So how impact is traditionally measured in academia is just by measuring citations. So if you write a paper and it gets very cited, it's understood as that it was a very impactful paper. And what we do is that we build the citation graph from papers accepted at EMLP and ACL. These are two NLP conferences. These are the two biggest NLP conferences since 2018, and we measure which papers cite which. And this way we get a data set of more than 185,000 papers, which is a big citation graph. And we analyze the citations between each other. And we also survey 138 members of the NLP community for their opinion to try to gain an understanding on what's their opinion on this area of research. So first, how did we actually build this citation graph? We have all the ACL and NLP data. We parse it into the papers, and we have the gold label on what's the track this paper has been submitted to. And there is a track that is associated to interpretability analysis. So we have labels on which papers are interpretability analysis and which papers are not. And this way we build a citation graph. So we analyze the citations between these papers, and we build graph like this, where we get which papers cite each paper. And we also get papers that are outside our data set. So these papers are not ACL and UNLP papers, and these papers are also not ACL and UNLP papers. And we're interested in the citations between the tracks. So we actually predict the submission tracks of these papers that we add using a classifier. So we augment our data basically uh, by predicting the labels of what the track of each paper are, like on these papers that are outside of our original dataset. And this way, we can actually get info on which tracks are well cited and which tracks cite which. And we can analyze how interpretability and analysis, the interpretability analysis track compares to other tracks. Um, but again, citation data does not represent fairly the impact of a research area. It's very hard to measure impact. It's a very hard thing to do in the literature. So what we do is we take a more holistic approach, and we also survey the NLP community for their opinion. So we just made a Google form and asked a lot of NLP researchers what they actually think on this area of research. And that's how we get all our data for this paper. And actually, I believe some people in this meeting have answered it. So thank you all. If you answered it and you put your name in it, you're in the acknowledgements on the paper. So I encourage you to look at the paper by the end of it. Okay, so some of our key results are that first, researchers build on findings of interpretability and analysis research. Also, that researchers find interpretability analysis work important. We also analyze what are the trends on the most impactful interpretability and analysis research papers. And we also try to answer what is missing in interpretability and analysis research. So what are the concerns that people have on this area of research, and how can we make this better? So, okay, the first result is that interpretability analysis is a well-cited research area. So if we analyze the citation numbers, uh, just comparing citation numbers can be unfair for a number of these different reasons. Basically, the distribution of citation numbers tend to be very skewed, and that makes comparing numbers not very helpful, because like a small percentage of papers can account for most of the citations of a research area, and that makes comparing things very unfair, because if you have one really impactful paper, then basically the whole area gets very impactful, and that might not be fair because the rest of the papers may be completely useless. Um, so we use a metric that is well known in the literature, which is the citation success index, to compare interpretability and analysis papers with other tracks. This metric is much better. It doesn't, I mean, it's not subject to the skewness of distributions, which is much better. And it's relatively fair in comparison to just comparing citation numbers. So how does this metric work? Is that, let's say we want to compare interpretability analysis to machine translation. We grab a random interpretability analysis paper. We grab another random machine translation paper. These are both published in the same year, let's say. And we compare the probability that the random interpretability analysis paper is more cited than the other random machine translation paper. So we do this by grabbing a lot of randoms interpretability analysis papers and a lot of random machine translation papers, and just compute the probability that these interpretability analysis papers are more cited than the machine translation papers. As you see, if you have one paper which is really, really well cited, it will not affect this metric by that much because it's just one paper. So the probability that this interpretability analysis paper is more cited is just not very affected by this one paper. And again, if you do this by to all the tracks that exist in these ACL and UNLP conferences, you see this is the results for last year, so 2023, and you see that actually only two of the tracks tend to have a result which is better for interpretability analysis. So only large language models and ethics tracks are below 50%. This means that their win rate against interpretability analysis is better for them because interpretability analysis only wins, in this case, 29%, and in this case, almost 46%, right? But all the other tracks are actually have a win rate that is above 70%, 50%. That means that interpretability analysis, more often than not, actually a random paper is more cited than a random paper of the other track. And in some actual research tracks, this difference is quite important. For example, in syntax, like basically you have a random paper of interpretability analysis, you have a random syntax paper, and you can bet a lot of money that the interpretability analysis paper will be more cited than the syntax paper. And yeah, so this distribution, as you see, is quite favorable for interpretability analysis. Uh, so yeah, only two tracks had favorable scores, and unsurprisingly, the LLM's track like is much more cited than interpretability analysis. This is no surprise because LLMs have been like a huge deal in machine learning. So the fact that they are very cited, it's not very surprising, and it should be reasonable. Um, okay, so one critique that you could have is okay, but maybe most of the citations to interpretability and analysis are only from interpretability and analysis research, right? So maybe the area of research is just citing itself, and maybe it's not making an impact on NLP as a whole. But when we see the citations for interpretability analysis, we actually see that the citations are mostly coming from other research areas more than just from interpretability analysis. So in this case, the gray line is the citations coming from outside interpretability, and the red lines are the citations coming from inside interpretability. And we see that basically most citations come from outside, which is a nice thing to have. It means that the impact is not limited to its own area of research. Um, okay, but even if this area of research is cited outside of interpretability analysis, it might be just in some niche research groups, and it might not mean that it's making an impact on NLP as a whole. Uh, so how can we actually get a better notion of importance in a citation graph? One metric is the betweenness centrality. So this measures the percentage of shortest paths in a graph that pass through a node. So let's say we have a graph like this. We can understand it as a citation graph. So each node would be a paper, and each edge would be a citation between two papers. And you actually measure the amount of shortest paths between pairs of nodes, and basically add a +1 to each node that is going through the shortest path. So in this case, very central nodes would get betweenness centrality score, which is very high. So for example, this 4 node here, which is very central, as you can see, it kind of links these two areas together, it gets a very huge centrality score. Some papers that are on the outside, for example, this 9, which is not very central to this graph, gets 0 centrality score. That means that absolutely no shortest path between two pairs of nodes actually pass through this node here. Um, and when you analyze okay, central nodes are in many shortest paths, and that's why they get a lot of like a huge centrality score. So in a graph, we can understand nodes with a higher betweenness centrality to be more important because we can understand that more information passes through them. Um, so when we analyze the actual betweenness centrality of our citation graph, and we analyze this in all the papers, we see that actually the interpretability and analysis papers tend to be very central. Um, just look at the actual x scale here. It's actually logarithmic, so these differences are quite a bit. Um Unsurprisingly, of course, the large language models track is very central to NLP because it's being used everywhere, so that's fine. But in second place, we have interpretability and analysis, which is very surprising, right? It's more impactful in terms of centrality that some traditional kind of NLP tracks like machine translation or machine learning or information extraction and retrieval, um, which is very important. It means that interpretability analysis is central to NLP. Um, okay, so now we contrast these results with the perception of the community, and we find that researchers also find interpretability analysis work important. So from our respondents, we get that most of them consider interpretability analysis work important, and for various different reasons. And this is considering that 61% of the respondents are not researchers in this area. So they are researchers in different areas, but they also consider mostly interpretability analysis work important. And we also ask like if the progress of NLP would have been slower or impossible without this area of research. And most of the people agree that the progress would have been slower, but not impossible. So in this case, for example, the yellow bars indicate if interpretability analysis would have been slower, and most people tend to agree that it would have been slower. But when we ask if it would have been impossible, most people tend to agree that it would have not been impossible, right? Um, Interestingly, the people who actually work in this area of research tend to be more skeptical of its impact. So we see that researchers that work on this area of research just believe it has not been as impactful as people who have not worked in this area of research. This might be that they have just better calibrated expectations on this area of research, when people outside of this area of research might see it as a very impactful thing because they have not really worked on it and they don't really know what its real impact is. Um, okay, so we now turn to answer the question, what actually makes an interpretability and analysis paper influential? Four of our authors annotated like almost 600 papers from our data. These papers include the interpretability and analysis papers that were recommended in our survey, most of the most cited interpretability analysis papers in our citation graph, the most cited non-interpretability and analysis papers in our citation graph, and also non-interpretability and analysis papers that are highly influenced by the most cited interpretability analysis papers. And out of these manual annotations, we draw some key insights. The first trend is that the recommended papers by people are mostly on representation analysis and a lot of mechanistic interpretability. So we got a lot of mechanistic interpretability papers recommended to us. So this is the type of uh, research that I've been talking about at the beginning of the talk, this understanding in the inner workings of models. Um, but when we see the actual most cited interpretability and analysis papers, they are more focused on the analysis side of interpretability analysis. So they are not usually mechanistic interpretability papers. Um, Also, papers which introduce metaphors tend to be quite impactful. For example, I've introduced a bit of these concepts. So these MLPs as key value memories and this residual stream idea have been very impactful in the community as a whole. Um, and also when we look closely at which papers were highly influenced by interpretability analysis, we notice that these papers are not very cited when compared to papers that are highly influenced by other types of papers. But there is a recency bias because interpretability analysis research is growing quite a lot. So most of the papers that cite these papers might be very recent, and that might be the explanation why they're not often very cited, because they just are not often very cited yet. They might be in the future. Um, so the main takeaways out of this research is that interpretability analysis plays a central role in NLP. Researchers do build on findings on interpretability analysis, and they find interpretability analysis work to be important. Then we ask, okay, so what is missing, right? Because we have a lot of skepticism. So what are the concerns of this area of research? All the data seems to suggest this is quite important. So why is there skepticism? Um, so a normal concern was the lack of big picture. Most of these models were just focused. Most of this research was just focused on very specific models and very specific takeaways and very small picture, let's just say. But there is no like big picture of, okay, what are we actually gaining from this research area? So this was our response we got on the survey. I think the focus should be on climbing the right hill towards a high level of understanding, instead of focusing on interesting individual behaviors, which many papers do nowadays. So yeah, one of the things we should strive for is just to have a higher level understanding in general and not try to focus on the details of it. So we compile the main concerns into a call to actions to hopefully improve ourselves as a research area. And our call to actions seem to suggest that we should think more about the big picture, strive for more actionable work. So it means that our research should have a practical impact and not just like insights that we cannot really use in practice. We also should center humans in our work. In our work, this means that we have to use more human evaluations because what is actually interpretable is a very subjective definition, and each researcher might grab its own definition, and that might not be grounded in the actual feeling of humans in what is interpretable and what it's not. Um, and also, we should work towards having standardized robust methods because most of the methods are just used for one paper and they are completely forgotten afterwards. So, actually evaluating and comparing different papers is very hard because there are not clear evaluation metrics between two papers. Basically, each paper grabs its own evaluation and makes it its own and is never used once again. So we should have more standardized and robust methods to actually do this kind of work. And that has been my talk. That's everything I've prepared for today. So I'm free to answer questions. I think I got 5 minutes left, which is just about enough, let's say. Again, you can ask in Spanish or English. I'm fine with both. I'll answer in whatever language you prefer.
Hola,
Hola.
¿qué tal, Tomás? Eh, Muy buena charla. Tenía dos preguntas. ¿Aló?
Sí, sí, te escucho, te escucho.
Sí, una quería confirmar nomás. Una de las cosas que dijiste es que la representación aprendida por estos modelos de lenguaje como que se mantiene constante a lo largo de las capas. Es el mismo espacio siempre. ¿Eso es
Mm.
así?
Sí, más o menos. O sea, los updates que se forman. Espera, espera. Los updates que se forman suelen ser graduales. Es decir, empezás con una representación. A ver si lo tengo. Ok. Empezás con una representación al principio, digamos, y,
Sí.
y cada capa va modificando las predicciones de cuál es el siguiente token, pero de a poco. Como que esta predicción suele ser de a poco y no es que en cierta capa, pam, hay un cambio tan como de 0 a 1, por así decir, ¿entendés? Como
¿Ya?
cada capa modifica ligeramente las representaciones. Para eso está el paper de Morgueva, que por suerte conozco, que
Ujú.
encuentra que cada capa promueve conceptos, pero de a poco. Conceptos como del estilo así, por ejemplo, como hay una capa que promueve conceptos de measurement, otra capa que promueve conceptos así, y de a poquito se van promoviendo estos conceptos capa tras capa.
Cuando dices promover es simplemente que esté metiendo información relacionada a esos conceptos en el stream.
Sí, 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 como la predicción de estos conceptos ligeramente se ve como promovida a lo largo de estas capas.
Oye, pero, o sea, no sé si estoy. Pero eso no implicaría quizás que el orden de las capas da un poco lo mismo.
Bueno, más o menos hay papers en donde sí intentaron de como alternar orden. Eh,
Ujú.
hay un, no siempre funciona tan bien porque hay como juego entre capas o entonces a veces como que meten información que va a usar la capa siguiente, por ejemplo. Entonces como que
Ya,
alternar el orden no siempre funciona bien, pero sí hay papers que intentaron como mezclar el orden de las capas. Uno importante, o sea, te puedo mandar después si quieres algunos en donde son interesantes, en donde hacen eso. Eh,
dale,
pero no es que da completamente lo mismo, pero sí más o menos puede funcionar bien.
ya, ok. La otra duda que tenía es cuando estaba hablando de estos sparse autoencoders.
Ujú.
no caché cómo hacía, o sea, porque lo que entendí es que la gracia es que tenía una representación que está como sobrecargada de alguna manera, porque queréis meter más features que dimensiones tenía, y después la proyecté en un espacio mayor para que sea más fácil separarlo.
Ujú.
Pero lo que no entiendo es cómo interpretáis las cosas en ese espacio mayor.
Ya, ya. Sí, ok. Entonces, la idea es esto, tenés este espacio chiquitito, lo mapeas en un espacio grande que es muy sparse, entonces cada una de
¿Sí?
estas neuronas está muy activada, otra no. Como lo interpretan es que
Ujú.
agarran un montón de texto y ven la correlación de en qué texto esta
Ah,
neurona es activada. Es
ya,
muy manual y
ya,
muy
ya,
cherry pick, y por eso hay muchas críticas al respecto. Em, pero sí es así.
ya, ok, ya, ok, entendido, ya. Ahí me queda claro. Muchas gracias.
Hola Tom,
Hola, hola, ¿cómo estás, Rafa?
bien y tú.
Bien, bien, bien.
Oye, te quería preguntar, desde ¿cómo se llama? Si vieron también el impacto de el área de interpretabilidad en otras, o sea, en otras partes de investigación que no sean NLP, como imágenes,
Mm,
eh, en general, digo.
mm, ok, más o menos. La razón es que muchos de estos papers que sí están por atrás y por adelante, ¿no? No solo son en NLP, también hay cosas en visión, en Machine Learning en general, pero nos enfocamos mucho en los trends en NLP porque nosotros, los autores, estamos metidos en NLP. Entonces, están en nuestro gráfico de citas, pero no vamos tan en detalle en como esas áreas. Y esa es una limitación importante del paper igual.
Bueno, y también, porque tú dijiste que no hay, o sea, no hay como un método de evaluación claro para decir esto es interpretable, esto no es interpretable. Pero tú o Mort tendrán alguna intuición o alguna heurística de algo que pueda decir esto es más interpretable que esto otro.
Ah, bueno, sí. Lo que se estuvo intentando o lo que la gente mencionó en los servicios es que preferían que haya muchas evaluaciones con humanos, que esas eran como más confiables. eh, pero de vuelta, no hay yo no tengo una buena intuición de cuál sería la mejor manera de hacerlo, la verdad. Es difícil y todavía hay mucha gente que intenta poner benchmarks y qué sé yo, y no muchos están agarrando vuelo en ese sentido. Es difícil.
Gracias.
¿Tienes preguntas en el chat?
Hay preguntas en el chat que no estoy leyendo ahora. Déjame ver. What are the main bottlenecks to scaling to bigger models? Ok, ok. Preguntan, lo voy a hacer en inglés. Okay. What are the main bottlenecks to actually scale interpretability analysis methods to bigger models? It depends on a lot of the methods. A lot of these methods actually rely on manual kind of analysis. So when we see research like this one, wait, like this one, where they analyze kind of how these the kind of concepts are encoded into the model. These are actually manual annotations. And that's, I would say, the biggest kind of bottleneck of this, that most of this research is very manual. So there's very little work on actually automating these kind of interpretations because it's very hard to actually do it. But there has been work on actually scaling these methods into bigger models. One actually interesting approach I've seen is that they actually use ChatGPT to generate annotations for this kind of intuitions that you can get automatically. It has scaled up quite well to some decently sized models. But again, it depends a lot of the method. I would say. I would say the biggest problem in general is this kind of manual annotation bottleneck, which is very hard to do. But there has been work into automating it. Partly is actually using another LLM to do the annotation for you. But there are other kind of methods that also struggle to scale up, and they have their own kind of research area into how to scale them up efficiently. It depends a lot of the method. I would say the most important is this manual bottleneck. Okay, por
Right,
ahí yeah, thank you for the question, by the way. Por ahí leí que alguien decía que Layer Norm hace que sea más útil pensar en el espacio de tokens como una superficie de una hiperesfera en vez de un plano. ¿Se hace eso en la práctica? Ok, sí, eso, yo no me ubico si eso, ok, eso tiene que ver con esto acá, en donde en este grafiquito mostré como que cada concepto es una dimensión por separada, ¿no? Eh, pero hay evidencia para sugerir que un concepto no es una línea recta, sino que un concepto puede ser un manifold en el espacio. Entonces, por ejemplo, digamos que este es el concepto de comida, tal vez comida no es un puntito acá, sino que es un área. Y tal vez hay como diferencias entre distintos lados del área de comida. Y no necesariamente es solo un punto. Eh, Hay evidencia que es así. Eh, ¿Cómo funciona en la práctica para, porque si esa teoría es real, ¿no? De que estos son manifolds en vez de ser puntitos, es como más difícil esta interpretación de los sparse autoencoders, ¿verdad? Porque estos están pensados para puntitos, no para manifolds. Eh, la verdad que no quiero entrar mucho en detalle porque es como medio complejo lo que pasa ahí. Porque lo que termina pasando es que estos sparse autoencoders encuentran muchas veces un mismo concepto, solo que lo encuentran como en, en distintos lados. Entonces podría encontrar un concepto acá, que está cerca, pero no el mismo concepto. Y a medida que creces la cantidad de dimensiones en tu sparse autoencoder, estos distintos conceptos van haciéndose más granulares. Una cosa así. Pero sí, la práctica no funciona tanto como puntitos, sino que son más bien manifolds. Y eso lo hace más difícil aún de entender. Por si acaso hablé de la palabra manifold, pero me acabo de dar cuenta que no es una palabra muy normal. Manifold significa una especie de subespacio dentro de un espacio. Entonces, en este caso sería como un área en vez de un puntito.
¿Es una generalización de un polítopo? ¿O menos?
Hoy yo no soy, a ver, yo no soy el matemático más. Yo no soy matemático, entonces no te puedo dar una definición tan clara. Eh, no sé la definición exacta, pero la podemos pensar en subespacio nomás. Sí, no te
Ya,
puedo
ya,
dar
dale.
esa definición.
Estoy pensándolo con la U.
No, está bien, está bien. Mira, si quieres preguntarle de manifolds, preguntarle a Mircha. Mircha sabe un montón. Bueno, pero creo que estamos a tiempo. Me pasé un poquito, pero creo que podemos ir dejándolas hasta acá. Cualquier cosa está o sea, voy a dejar mi mail si alguien tiene dudas, pero, y sí, creo que lo estamos grabando y lo deberíamos subir a algún lado. No tengo idea dónde, pero en algún lado va a estar. Eh, Así que eso, voy a dejar de grabar, de compartir. Eso. Y de verdad, gracias a todos los que vinieron. Lo agradezco mucho. Para algunos es bien tarde, eh, así que agradezco estar acá tan tarde. Agradezco mucho.
Muchas gracias, Tom. Buenas noches.
Bueno, nos vemos.
Gracias.
Gracias.
Okay.